Okay, so today I'm going to describe this particle. First of all, before starting this presentations, I would like to thank you, Ursula, especially for inviting me to give this talk at the TXRF platform. This is a European chapter. So I would basically the title of my talk, we decided, okay, why not give the talk on the particle size and temporal coherence effect, the temporal coherence property is a primary X-ray in TXRF. So how the temporal coherence property of the source basically play important role in TXRF analysis, how they affect the analysis. So let us move. So this is what the plan of my talk. So I will be describing the indus facility, where we are working. And then I will provide brief introduction because you already know all these things. We all are expert from XRF, so we all know. And then I will describe the BL16 facility beamline, BL16 beamline, which we have set up in the industry facility. What are the capabilities of this beamline and various silent features, different techniques which are available on this beamline, XRF, TXRF, microimaging, X-reflectivity, and grazing incidence, X-fluorescence analysis. And then finally, the topic of today's topic is effect of particle size temporal coherence, which I will describe in detail, and then application. So, okay, so this is what the snapshot of our facility, which we have, indus facility. This is accelerator synchrotron source. Basically, we have in India we have two synchrotron source, one indus one. First, this is 450 MeV source. Electron energy. It provides synchrotron radiation and energy in soft acceleration, right from 300 eV to 900 eV. So this is absurd. Okay, so you see, this is two buildings are there. So one, this is Indus 1, and this is slightly, because this is a small machine, so we have slightly small building. And then this is Indus 2, which is bigger machine. This is 2.5 GB electron storage ring, and it provides energy mostly in the hard acceleration, soft acceleration, both cases. It consists of winding magnet as well as undilators. So this is the scheme of Indus SR facility. So basically, we generate the electron from a microtron, and then we put this electron beam in a booster ring where we boost the energy from 20 MeV to 450 or 550 MeV, and then because this Indus 1 is basically a small source, so it is soft access source. So normally we allow the electron beam of energy 450 MeV directly from the boosters. But if you want to inject the beam into Indus 2 storage ring, so we normally accelerate the electron beam up to 550 MeV. Then through the transverse line, this we transfer the electron beam in Indus 2 ring, where we further boost the energy of this electron beam to 2.5 GB. So this is the operating parameter of Indus 2 source, 2.5 GB, and maximum current it can hold around 200 mA. And the critical wavelength of the source is 2 angstrom, around 6 K. So this is what the facility's background of the facility. So now I'm describing interaction of X-ray with the matter. So you know all these things because the X-ray source, when you allow the X-ray to fall in some sample, so there are three processes that go on. First, the X-ray may scattering elastically, so the photon of energy as new gases come, and then it's scattered with the same energy, but there is some change in angle. So the energy doesn't change, the only angle is changes. So new dash is equal to new dash. So we have described new dash, but new dash is equal to new dash. So frequency doesn't change. That means energy doesn't change. The only angle of the scattering of X is changed. In the second process, inelastic Compton scattering, basically where the energy of the incident after scattering changes. And as with theta as well as, and then another options where when the electron interact with the inner cell electrons, K cell, L cell, then the inner cell electron emitted as a photoelectron. The vacancy is created over here. Basically, so for example, this is what, suppose the electron incident photon is coming, this interacts with the K cell electrons. So the vacancy is created, photoelectrons comes out. And then the uppers, because this vacancy is there, so the upper cell electron jumps into this lower cell. And finally, the difference of energy of electron released as a fluorescence photon. All basic things. And second process, because there are different competitive processes are also there. The OJ electron structures, OJ electrons, OJ effect can also occur. So again incident photon is coming. It hits the inner cell electron. The vacancy is again created by the absence of photoelectron. And the inner cell electron jumps into the inner cell. And the vacancies, which is created in the upper cell. And the difference of photon, basically difference of energy is released as a photon. Now this photon again excites the inner cell electron. So it doesn't come out from the atomic environment, but internally it excites another electron in the atoms. So it is ejected as a OJ electron. So this is a electron spectroscopy. Normally, most of the people they do the OJ electron spectroscopy. OJ electron spectroscopy is a very good technique for, especially if you want to analyze low Z element analysis, which is quite effective. So these are the basic principles. So we normally use all these things. So it's kind of fluorescence photon emitted because of the electron transfer. And this is typical spectrum normally we see. And this is scattering, because the scattering also occurred in X-ray whenever we excite the sample by X-ray. So the X-ray basically is lot of background or scattered X-rays, and then we see the fluorescence. So this scattered background is major problem. Fluorescence technique. It's a fluorescence technique. This is what this. So basically, the background limits the detection sensitivity. So that's why we do apply different techniques. For the XRF limits the detection sensitivity of XRF something around ppb level, ppm level. But if you allow the TXRF, then you can achieve around ppb, slightly less, slightly better if you have synchronous excitation source. So now this is what the basically considering different. I think PhD student may also be there. So this is what the nuclear density, whatever size nuclear density. What is the nuclear density? So you know this size of the nucleus is nothing basically. The nuclear radius of the nucleus is something r is equal to r0 power minus 1/3, where a is the atomic mass, and r0 is basically this constant. This value of this 110 power minus 15 meter temperature. So if you put all the things, then you determines that the mostly the size of, for example, I have described this, for example, uranium 56. If you calculate all the things, then you have the density of iron something 3.8 grams. And similarly, if you have uranium 235, then a power 1/3. Basically, how it depends on the atomic mass. So you see, there is not much difference. If the atomic size increases, effectively the density of the nucleus remains same, more or less. So how to realize how much nuclear density is high? So just provide basic comparison. So if you collect seawater of 10 kilometer wide, 10 kilometer wide, and 10 kilometer depth, if you put into a small volume of the order of 1 meter, 1 centimeter cube, you will receive this kind of density. So this is a direct comparison how much density you can have. So it is very high. So you know, this is what I am going to describe. Basically, if you see in all the things in the nature, for example, if you consider the atom, basically you have the nucleus, then you have the first electron, then another, then again we have the space, then second cell, then third cell, like this. So that always there is some space. So you have the particle and there's some space. Similarly, if you consider a solar system that has several planets, so you have the solar mass and then different planets, and solar and planets in between there is space. So that's what you see. So this is the axis is very important. Whatever the nature has created, it is very good. It is important because otherwise, if there is no space, then you cannot imagine the life. Because to sustain the life, you must have the space. This is true even if you consider the Milky Way. So there's a lot of space and some mass is there. So this is also, that's why it is also important day-to-day life to consider that everything is possible because of this space limitation, space availability. Now the X-ray fluorescence lines already you have. If you analyze all these things, then you can say this is a very complex spectrum. Normally FK line, for example, K alpha and K beta. So because fitting is also very important. If you want to analyze, if you want to do the analysis, it's very important to very precisely analyze the fluorescence peak area. And you see this is K alpha, it has two peaks, K alpha and K beta. Similarly, AGK, it can contain K alpha, again split into a different K alpha 1, K alpha 2. So it is very important to decide if you have the several elements in a sample, then again there are a lot of mixing. So people, they use the phi MC software. So if you do not carefully put the basically lines, you do not consider the K line, L lines, whatever. So it is very important. You might get the error in your intensity analysis. So that's ultimately it affects the quantitative analysis. So similarly, the L cell structure again very complex. So again, it is very complicated, especially the quantitative analysis. So now I'm coming to the execution beamline. So you see, so this is what we have. So before going to the execution beamline, so this is typical. Just I'm giving the example of billions. What are the billions? So billions is nothing. Basically, it defines the photon per second per millimeter square per millirad square. 0.1%. This is typical term normally we use the synchrotron community. But photon brilliance is nothing. Basically, you define whatever the basically whole solid angle of the light which is emitting, and if you divide the source size, then you get the brilliance. For example, this candle light. Normally we get the candle light in. So typical brilliance from the candle light is 10 to the power 3. And similarly, if you consider 60-watt bulb, the typical brilliance in 10 to the power 5 to the power 6. And if you consider laboratory access source, conventional access source, the typical brilliance, normally we have 10 to the power 8. If you allow the rotating and generating something, then you might have the 10 to the power 9 brilliance. And our sun basically provides a good brilliance, 10 to the power 10. And this is in our synchronous radiation source, something like 10 to the power 12, 10 to the power 30. And this is our basically our eye, basically the limit of our eye that can handle the amount of brilliance, basically this lies in 10 to the power 7 something. So that's why we cannot see the sunlight directly, because our eye is not capable to handle such high amount of flux, photon flux. And people are talking about the second generation, not second. They say that the second generation is not sufficient. Even we have to move to the third generation. We have the undulator, even fourth generation. Talking about the flux of the order of 10 to the power 20 and 10 to the power 26. I don't know what type of flux they are planning to use, because this is so high density, your sample may want evaporate immediately. So this is the layout of our beamline that I'm in charge of this beamline. So you see the electron is moving in the storing, and then the final radiation is emitted. So we have the DCM optics, where we monochromate the silicon 1 monochromator. So it is a very good resolution. Then we have SILIT, and then we also have the focusing optics, KB optics, where we generate the microfocus beam. And we have provided the option, we can remove this KB optics from the beam path, so then you can have the parallel, this collimated beam, not focused beam. So we have both options, collimated while the focused beam. So this is what the typical we are using the TXRF in the setup. Normally right now we are using the air environment. Recently we have installed two vacuum chambers where we do the LSST in the vacuum environment. So we have the both TXRF assisted vacuum chamber and XRF assisted vacuum chamber. So for low jet. This is what the principle of the TXRF. And this is the basically initial results received. So this is the incident beam size of the incident beam. So we allow around 1 millimeter by 1 meter square before KB optics, and then it generates around 2D focus. The mirror size is around 200. Yeah, 200. So basically, so this is what the typical application we have allowed. So we analyze, just test our capability of our beamline. So we use a tile sample, archaeological tile sample. This was 500 years old sample collected from the old church of Old Goa. And so the people were interested, users were interested. What are the different elemental compounds in different colored region, and what are the composition system? So we realized we focus the experiments at this place, white region, blue region, black region, and realize this is basically by adjusting the composition of iron, cobalt, nickel, they have to create a different colored region. And for the polished surface, they allow the lead basically to generate the very polished surface. So we were not knowing that the lead is also very toxic. And then we did some cross-section analysis. So the cross-section analysis so that this is different layer. There are several layers of lead they have allowed before generating the polished surface. And this is the iron distribution. So iron is coming from the soil. So this is clearly showing the layering structure of the lead coating before generating the some color texture. And then we also tested this. You see, this is what the so this is copper TM grid structure, copper grid structure, which normally we use in translucent microscope. So we generated the fluorescence image just for test and calibration. It's whether the resolution, what kind of resolution what we're getting from it. So this is the fluorescence map of the copper K alpha, and this is the SEM image, optical image of the copper grid. So you see, this is what the typical 1:1 is here, and this we also calibrated what is the photon flux number that we obtained. So we have used both the collimated and unfocused and collimated focus. So focus is at less, but collimated is focus. But typically of the order of 10 to 7 to 8. So again, this is what we have. We did this analysis. Always with PRC, so this is not very important, but yeah, this is important. So we analyze this with volume oxide fluid samples. Basically, this is what it contains. So this idea behind all this analysis is to whether to determine the distribution of the whether it is homogeneous or non-homogeneous. If it is non-homogeneous, it generates basically localized heating effects are there. So ultimately, it results the cracking of the pellets. So this kind of thing. So we analyze two process order PMC rule by which they are prepared. PMC kept. So just to idea was to whether how the methods are efficient, what are the disadvantages, and which is all. I will not describe all the details in more detail. There's paper is already published. So this is so. In one case, we obtain a lot of inhomogeneity in thorium distribution. In one case, in one of the methods, we realized this is quite homogeneous. And homogeneity, we found that in the CFP fuel pellet process, there's this negative, basically, correlation. So where the thorium is high, the iron is less. Similarly, in PMC fuel pellet process, the thorium, there's positive correlation. When thorium is high, the iron is also high. In non-infant, we found that around 60%. And second case is 10%. Okay, so now with this, I'm coming to some environmental analysis. So you see, this is what. So yeah, so you see, in India normally we use this basil leaf for basil leaf is very popular whenever we take tea. So this the idea was to whether what are the different compositions, because there are two types of basils. Normally we have in India, the Rama Tulsi and Krishna Tulsi. So this is Krishna Tulsi is basically slightly black in color, and Rama Tulsi is slightly greenish. So the idea was whether to distinguish what is the concentration, what is the basically, is there any difference in elemental composition? So this is the typical spectrum. There's iron, copper, nickel, and etc. Potassium is also good, calcium, so it's strong. And this is another leaf. So you see, so there is difference in basically the intensity of iron. So basically, it's iron ratio of the different element. So this may be some medicinal effect, some medicine. But anyway, so this also we applied another application. We analyze the groundwater. So whether groundwater contains some water type of different elements are there. So we quantitatively analyze. And just to compare whether it's groundwater, what are the different elements in groundwater, and it has the direct comparison with the coconut water. Coconut water is very basically coconut fruit, and it contains water, which are really rich in minerals. It contains a lot of minerals. So normally a lot of people in India they take the coconut water. It contains a lot of potassium. Basically, all the fruits basically they contain good amount of potassium. So it is also true for water. So you see that potassium, calcium, not only because the potassium is there, so you also realize bromine, rubidium, and iron, manganese. So several elements are. They are very helpful for. They are very useful for the water. So this is what. So we then realize how they are. What are the concentrations of different elements? In one case, we studied the water, groundwater, at different three locations. So in one location, we collected the water from our hometown, and there's one from the Mathura, and there's the third 600 kilometers away from the Mathura in Indore. So we analyze the different concentration, different element. Finally, we realize okay, this water which we have collected, Mathura, basically also treated with the RO, reverse osmosis, and we realize this potassium concentration is very high. The potassium concentration is in the water MTJ is slightly high. In similarly, in this is not without this as it is groundwater, and simply coconut water. See the potassium content in here. If you contain this Narmada water is 0.92, and if the water treated with the filter, the RO filter, then this potassium slightly increased. This is again groundwater. It's more or less similar, 0.9, 0.4 something. And coconut water contains a lot of potassium. So why this water is similar? Because we use the groundwater and then treat it with the RO filter, and the concentration of potassium increased. So why? So the reason is basically sometimes normally the people, the RO manufacturer, they use basically some chemical component, chemical ingredient to filter, basically just to transfer the ion exchange method they allow. So basically calcium ion basically convert stores, and basically potassium ion basically increased. So that just to maintain the component, different compositions. But this is not good. So this is what basically just to compare what are the different elements. Similarly, if you see the bromine is also very high. Rubidium is also something like rubidium is concentration very less, but even in the coconut water is very high, around 2,000 times high, even. Now, so for quantification, normally we use because the quantification is very tricky method, because there is no, I would say, if you purchase instrument, then you can have the quantitative software. So there lies. But this is also not true, because when you analyze that, when you do the analysis in the, especially in synchrotron field, then you change the analysis. And all the commercial software they calibrated for certain conditions, for certain distance, certain excitation, something. And normally we do the analysis for different. Sometimes we do the analysis in EDXRF mode, sometimes TXRF mode. So we have developed our own the IA sample we analyze. So here you can change the energy, whatever energy you want to put, you can change. But whatever the mode you want to apply. For example, if you do the analysis for EDXRF, click EDXRF. And you can also define the detector parameter, custom settings. Most of the custom settings. You can consider, for example, if you have the you can analyze at the same time how many elements, around 20 elements, up to 20 elements simultaneously. So finally, if you show the reds, then you appear the windows appear something like that, and use the concentration different ppm, whatever the percent. They also may be very useful because we have analyzed for the nuclear metals as well. So we just tested the software whether it is working properly or not. So this we have participated in IA activity. So in last year I participated. Last year, but last year. So determination of major and minor trace is 77. So this is what. Yeah. So this is what the analysis is good, but normally if you are in this range, this is quite good. But this is also not very bad. But yeah, some of the elements visible. And if you compare the R and Z score factor, this is the basically normally people do not share their basically code, but so this is what the Z and Z score of different laboratory codes. So this is a laboratory code. Our laboratory code is 209. So you see, this is our the one precision of TXRF program over here, and this is a precision of and normally this region, normally people are utilize this neutron activation. Because the TXRF analysis, there is no problem with the X, basically quantification. Basically, the peak area determination is major point. If you want precisely determine the peak area intensity, yeah, a spectrum process, fitting process is not good, then you might have very high errors in quantification. The calculation errors not very high, but spectrum fitting process may be. So one should be very careful while especially for the small peaks, or if there's a lot of over mixing, lot of element mixing. So this is again the R square. Again, comparative study or software. So now I am coming to the analysis of nanostructure. So what the why using it? Whether it is possible, because normally people use the exophotosynthesis technique for the bulk analysis. This is quite popular. But whether we can analyze the nanostructure, some people they have already done. And so there are nanostructure material with thin films, nanoparticles, other nanoform. So normally we use the nano thin films. So nano thin materials basically what happens. We normally interested in what is how the concentration profile of different element is changing as a function of depth, and also we want to do the analysis non-destructive without destroying the cells, because we don't want to destroy our cells. So normally people use the axis reflectivity. Resistivity method are also applied. GXR, axis-static, neutron reflectivity. So these are the typical non-destructive methods. And reflectivity is very good sort of technique for the thin film determination because it provides very high accuracy. But you cannot have any information about the elemental concentration. Whether if the elemental concentration changing as a function of depth, then it is not possible to apply this. But if you allow the XRF and GXRF both techniques simultaneously, then you can have the good precision. So the GXRF basically provide the good precision about the elemental analysis, and the XRF provides the precision about the thickness determination. So combined analysis is very good. So by using the exoflectivity, what are the parameters that you determine? So basically, the exoflectivity provides the thickness. You can precisely determine the thickness, and roughness, if there's something roughness is changing, and if the density is also changing as a function of depth, density character. So, for example, this is the reflectivity profile. It's a simulated reflectivity profile of copper oxide, and copper. So you see copper oxide on top of copper and substrate. So you see there's several oscillations are here. Typical oscillation, if the copper thickness of the copper is slightly high, then this small oscillation, occasion oscillation bit is small. This gives the information about the copper, and you see this overlap region also. Some big oscillations are also there, and this big oscillation basically provide the information about the thin copper oxide layer. So because we are analyzing simultaneously both the things, so that's why we have the overlapped reflective profile. So we applied this technique for this is the spectral results, titanium silicon oxide. This is the reflective profile fitted with the GXR program. And this is another technique, another sample. Yeah. So this is what the reflectivity at 8 kV is, and this is what the 8 kV of thin film. And XRR and GXR analysis what simultaneously. We were measuring the reflectivity as well as flow simultaneously. Because it is very important, you have to measure both the signals simultaneously. If you do one by one, then the individual error will be there. So just for the simultaneous analysis, we have this program. So you in one window, you see that you can load the exponential data, and then you can fit. So simultaneously, you see that whether this fitting is good or this fitting is good. Whenever you have the convergence, then you find that okay, you have good fitting as well as good fitting for the fluorescence profile. So you can adjust the parameter, and also provide the facility structure type. If you're a multi-layer structure, then you can define a multi-layer structure. If independent layer, then you can have a different layer. Beam footprint you can also consider in the analysis. And it also have some ID, basically can give you some electron field distribution and effective density, effective electron density. So you click on this, provide how the electron, basically electric field is distributed above the surface as well as inside the materials. And this provides the electron density profile, how the electron density of the system is changing as a function of depth. So this is what good thing that normally we do the simultaneous. So this is what important also. So, and because this normally we do the analysis simultaneously. So if there is any problem, for example, a small change in, because if you do the reflect fluorescence profile alone, and if you're measuring the fluorescence signal from that particular layer, then you can catch this error. For example, we have analyzed a tungsten carbon material, and somehow due to some error, one of the layer is slightly large in thickness, and we were trying to fit this analysis. We could not achieve with the similar model. Then we realized there is some error, something problem. So then we put the independent model there, and when we allow the one thickness of the slightly large tungsten layer, immediately we got the fit. So basically, the fluorescence signal is very, very sensitive to the layer thickness. But if you are getting the, if you are also measuring the fluorescence from that particular layer, so if there is any error in the thickness, you can immediately it will reflect the fluorescence profile. So this is what the result. So you see, this is just to confirm whether we are measuring a good signal or not, whether we are getting the reliable results from your program. So then we did the TM analysis. So we realized this one of the thickness is slightly tungsten layer is slightly large, but in it this top layer and this bottom. So slightly in the bottom, the thickness of the tungsten was large, and we somehow corrected this. We analyzed this using the GXRF. Just to confirm, we did the TM results. Now, so thin film is okay. One can do the thin film analysis using the GXRF, TXRF. Whether the implanted surface, similarly, typical applications of the GXRF technique can also allow thin film interface nature, diffusion study. If the layer are diffusing between each other, then you can also do the GXRF. Impurity depth profiling, this can be done, but several people are also doing this. So impurity depth profiling, unimplanted depth profile can also be done. Ion beam irradiation. Whether if you irradiate the sample, for example, if you irradiate the sample with thin film sample, thin film, any metallic thin film, one ion irradiation, then you can have whether the structure of the thin film changing, whether the mixing the surface interface is changing, or the two layers are mixing, whatever. So this, so basically, ion irradiation induced changes you can analyze. And similarly, magnetic thin layers, multi-layer structure can also, because it's slightly less impurity. Even some impurities somehow get introduced in any layer, it can change the magnetic property. But if you want to analyze how to analyze, so then you have to use the GXRF technique, and it is very useful. So now up to now we have described this thin film, Stamper structure, doped structure, ion radiations. So now I'm coming to the particle side. Particles. So where this particle, in the incident beam acceleration, you have the mixing of the different particles. The particle A and B, if you put together on top of substrate. So now you want to analyze what is the size of the particle A, size of the particle B, and what is their distribution profile. That means what is the size distribution, and what is the shape. It's also possible by XRF technique that you can determine the shape also. But because the fluorescence profile is quite sensitive to the shape, which we are going to describe. So, and this normally typically one can analyze particles in the 1 nanometer to 100 nanometer range, well-defined shape. You can also distinguish what is the shape of the particle. You can also distinguish what is the distribution of the particle, size distribution. And conventional technique, normally people use SEM, AFM, microphotometry. But the disadvantage of GXRF technique is it is elementary technique. So basically, if you have a mixture of the particle, then you can distinguish distinctly what is the size of particle A, particle I, for example, iron, gold, iron. So this is old work which we have already. Still, you see, this is the, if you calculate the access field intensity, you can sharply see the boundary, this critical angle. Okay? So if you put a particle over here, you see the particle is, if the particle is occupying how many fields it is occupying, you will see the oscillation accordingly. if it is occupying 3 standing wave fields, you see the 3 oscillations. So for example, 50 nanometers. If you have slightly increase the size, you can have slightly set. If you are occupying only one oscillation or 2 oscillations, you have the 2 oscillations. 2 standing field, basically standing field materials. So this is rigorous mathematics I'm not going to describe. This is already done, and we have already published this. So mathematics is quite complex, but you put everything in the computer program that is quite easy. So now the question is, because this simple TXRF analysis can be used for determination of the particle 10 nanometer and but how you can determine the particle less than 10? So initially we had tried if you can use the some multiple structure, because if you see in TXRF field, below TXRF field, the standing field is slightly, the thickness of standing field is slightly, so you can use that field for analysis of nanoparticle greater than 10, 20. But if you see the standing field in the Bragg region, this is slightly less, quite less compared to the TXRF standing field. So that field is slightly less, so you can even it allows to analyze the smaller size particles. So we have done this thing. So you see, this is what we have 10. I don't know whether it is visible. So by using the multilayer assisted field, we can analyze particles size up to 5 nanometer, 5, 10, 12. This size, no issue. So we confirm this our technique. So you see, this is a 5 nanometer particle on top of a silicon substrate. So whether it is 5 nanometer or 10 nanometer, 20 nanometer, up to 20, there is no different distance. But if you 5 nanometer, you see this is reflectivity doesn't give anything. See, there is nothing. And fluorescence, you have this kind of thing. And thin film, this kind of things you can achieve. So, but if you have the nanoparticle 5 nanometer, this is theoretical, this is experimental. So you cannot distinguish whether it is 5 nanometer or whether it is 20 nanometer. But if you allow the multi-layer structure, then you see it's 30 nanometer. You can have clear 2 oscillations. Similarly, 5 nanometer, 6 nanometer. You can have this kind of. So this is a reflexive, basically fluorescence. It is not a multi-layer fluorescence from emitted from multi-layer structure. This is particles are put on top of multi-layer, and this is the fluorescence profile of the particle, cobalt particle. So you see, by fitting this by Bragg region, one can determine the size of the smaller size. This is the method basically describe how you put the particle. So you first discuss the particle in solution, and allow some alteration, dispersion, and then directly put the particle in surface. You want to have the homogeneous coating, then you can use a loud coating. Now, coming to the shape of the particle, whether the fluorescence technique is sufficient enough, whether it has the capability to analyze the nanoparticle shapes. So, for example, there may be different type of particles out here: cylindrical shape, spherical shape, pyramid, half surface, so forth. Now, if you want to analyze the particle shape, then you have to model the fluorescence profile by taking into account the shape profile. And how to determine the shape of a particle is nothing. Basically, you just cut the particle to equal half. Whatever the size, this is the shape profile. So this is the shape profile. You can easily cut. So if you have the spherical particle, you can try with formula G. So this is the shape profile. Shape profile is nothing. Basically, just cut the particle equal half, and you can obtain the shape profile. And mathematically, you can model it. So just to, I have done some calculation. So we have considered a spherical particle, average size 100 nanometer, and the RMS deviation particle is just 10 nanometer. So you can see this is the profile that we obtain closest week. And this is the average particle size distribution. So it has mean size 10 and 100 nanometer, and average RMS deviation of 10. So this is the profile. Now, if you same size particle, average particle size is same, but the distribution of particles slightly changed. See here, this 10 nanometer, now it is 14 nanometer. Immediately, if you compare the two graphs, the fluorescence profile is also changed. So that means you have the fear sensitivity in the TXRF method, where you can determine the deviation of the particle size distribution. It is possible. Similarly, if you consider, because in early physics I consider spherical, but if you consider the rectangular, or you can say cylindrical type of nanoroid, then you have the profile is nothing basically one, because everywhere basically the size is not changing, vertical size. So you see, this is again I have considered 100 nanometer average size, mean size, and RMS is 10. And this is the process profile in case of the cylindrical particle. If you see, this is 100 nanometer particle, 10 similar parameters, but the shape is different. So this kind of spherical case, and this is for cylindricals. Parameters are same. So that means the fluorescence profile is also sensitive to the shape of the particle. And similarly, in this case, we also consider. So if you slightly increase the dispersion, RMS deviation in the particle size, then lies fluorescence profile also changes. So ultimately you can conclude the fluorescence profile have the capability, then it can determine the size, mean size, particle size deviation, the particle size distribution, and also the shape. Then so we experimentally analyze the 30 nanometer gold particles. You see this we have we have determined this. We found that determined side was 13 nanometer and sigma variation 2 nanometer. And then we confirmed the AFM microscope, also electron microscope, and utilize the method is quite useful. So now the topic is, because slightly I have a lot of things, but I can see this. So now up to now we have considered how the particle size, how the particles basically influence the fluorescence profile, and whether the fluorescence profile has the capability to analyze particle information about the particle. So that is that we have proved that it is a capability. Now, how the temporal coherence? Temporal coherence means the beam which is coming. For example, if the beam is coming, and this is the conventional normally we use, we assume that it's already one Wallen have described this thing. We have also described how whether this is this triangular region where the two beams interferes, whether excess field created is homogeneous, whether it depends on the monochromaticity of the incident wave field or not. So if you consider, normally we consider the lambda is basically single lambda, only single lambda is correct. But in fact, in experimental, you cannot achieve single lambda. Always you have some distribution, only it has Gaussian distribution. So, so it should have something, because so temporal coherence also have the role to play in this time. If you do not consider the coherence property or temporal coherence or monochromaticity of the incident beam, you cannot truly describe the existing in this triangular region. So basically, this is the method. This is all the mathematics thing. So if you want to determine the intensity as a function of theta at particular height j, so you have to just take the modulus vector sum and vector addition. And then if you want to have the intensity, then make it squared. So if you detail out, you can just explain it more detailed way. Then you have this kind of expression. So now this additional term is coming, delta path. This is path difference especially. So this is path difference, or you can say this is complex degree of coherence, temporal coherence. Degree of coherence is also important. Normally we consider this because the single lambda, so degree of coherence is 1 because there's nothing. So single lambda, so there's no. But in fact, it is not true. So you have to put the degree of coherence as a function. This is new to the phase of the E field ratio, electric field, the phase of the E field, so electric field, reflected field divided by the incident. And this is a QZ and QZ vector. The QZ nothing basically 4 pi sine theta y lambda, and Z is the height. And you can follow. So this is what the expression for the incident wave field is. So the technical things. Again, maybe there may be some people who are from the chemistry background also. But anyway, so this is So if you accurately want to determine how the nature of the existing field in this triangular region, then you have to consider the monochromaticity of the incident wave field. It is very important. And this temporal coherence length basically described by the lambda square lambda, basically you have to just multiply the lambda. And then if you want to define, because you also need a complex degree of temporal coherence. So the complex degree of temporal coherence basically that the E field average time dependent basically field intensity, incident field, and the cross dot product of the reflected incident and reflected field, and then you have time average, take the average over time, and then similarly the electric field time dependent electric intensity or incident field. This is intensity, single. This is intensity, but here is the field time average field. So if you solve it more in detailed way, then you have this kind of expression. But again, this is very complex. Again, I have already said that we put everything in computer. It's very simple. So you see, this is for example, if you use a DCM double crystal micrometer or you silicon one micrometer, what's very high micrometer around 500 or 1 EV resolution 10 kV. So this is one very good micrometricity. In that case, the intensity basically you can have good basically fringe pattern over the very up to large height, around let us say 10 micron, no issue. But if you slightly decrease the monochromaticity of the incident field, the field is not basically, you cannot have the over the full height basically this triangulation. Up to certain height, the two beams interfere, and after that they do not interfere. They just make the sum of the two terms. That is 2 terms. Double intensity. This is 2 terms. This is 2 terms. Here it is 4 times 0, 4 times. Or slightly to also change. So from 0 to 4, 4 to 2 times, and also 3 times, 4 times, 2 times. So this is what we should take into account. So for example, if you allow the monochromaticity 6.22 to this very low monochromaticity, then you have this kind of field, and the temporal coherence length 0.51 nanometer, and the height which this temporal coherence length corresponds to height of 120 nanometer. And here the monochromaticity is very high, then this Z is something 10 micron. This is the demonstration 3D forms. This is what some of the things. So this is a critical boundary, below critical angle, you have the well-defined fringe pattern, the standing field, and this is what where the monochromaticity is low. Then you have this is a critical angle boundary, is below critical angle at some height. This is the height where it is height. So at some height up to this 100, we have a good amount of high intensity standing field, and slightly it is decreasing. And at large height up to 100 to 250 nanometer, it is just simply sum of the two intensity. So if we have the particle size of 200 nanometer, 250 nanometer, then you have to take into account this temporal coherence in your calculus. Otherwise, you get some error in your calculus. So just to check whether this is working. So this is what again we have analyzed. This is a structure which we have analyzed. This is LV film structure where the chromium layer is here. Chromium and then gold layer, and then on top of we again coated the zinc. So chromium, gold, zinc. So zinc layer is 33 nanometer only. So we analyzed because this data was collected at International Laboratory in US, and Michael Batch, you might be known Michael Batch, they have collected this. So then we decided why not to do, and whether it is possible that we can have some theoretical model which can describe this temporal coherence model. So this was quite old data, but we fitted in 2015 the power distribution. So you see, this is the data which we have collected. Same sample, we have measured the fluorescence profile at 5,000 monochromaticity, zero power, and this is what the fluorescence profile. In one case, decrease the monochromaticity of the incident field. The fluorescence profile changed, and in another case, third case, we again further decrease the monochromaticity, and we see the fluorescence profile change. It's quite sensitive to the monochromaticity of the incident. It means temporal coherence property play an important role in the analysis. In thin film also. So see, because this why this is come, because you see the intensity change. But if you see the zinc is somewhere here, so the field is somewhere we see that if we have the 1 oscillation, 2 oscillation, 3 oscillation, 4, 5, 6, 7. That's why 1, 2, 3, 4, 5, 6, 7. Now, if you decrease the monochromaticity, the intensity of this peak intensity is changing. Peak intensity is also decreasing. So because I have already described, because the beam is coming and reflected, and it is again interfering. So there is also multiple reflection takes place. So for example, this is the incident beam is coming and is reflecting, and again interfering with the incident wave. So this is the extra path it has taken. Okay. So if the height, the height which is traveled by the beam is slightly more than the temporal coherence there, then it will not in the same phase. Then you will not have it will not constructively interfere, and you will have less intensity. Then multiple reflection, again, because it is going multiple reflection, so again and again interfering. But because of the reflection, it is also some kind of absorption is also there. So that's why you can consider something like that. So you put that absorption because multiple reflection is taking place, the beam is coming reflecting here, and also absorption is taking place. So that means that the height is good because the beam is traveling from here to here. So taking extra path. Similarly, the beam which is reflected from here to again just coming back to the bottom side. So the beam again interfere here. So on the both sides, the top and bottom side, you have the less intensity. So that's why you see the intensity is decreasing. Now absorption also play an important role in TXRF analysis. So this is what we have done. We put the samples on the multilayer surface and allow incident. So we disperse the particle over a large surface area. Oh, sorry. Right. Okay. So you see the absorption. If you consider the absorption effect, so absorption basically decreases the forces intensity in the TXRF region. And if the particle size is bigger, then you see no oscillation. If the particle size is small and comparable to the external side, then you see the oscillation. And if the oscillation or if the large amount of even the particle size, even if you have the nanoparticle, even the large amount of nanoparticles are there, then again you will see the absorption. So the particle size as well as the absorption effect will both play an important role, and they will decrease the intensity of the oscillation. So you see this oscillation decreases in the TXRF because you have the high intensity of that region because the absorption effect is less at the region, but here because the lower because the beam is traveling over the long path, so the absorption effect is very large. Again here. And see, this is what we have done the nanoparticles. So whenever we do the TXRF analysis, you cannot assume that every particle will be in the micronesia, because you will have certain probability that some particle may be in the nanoparticle. That's why you see large error TXRF analysis. It is already known. So we have considered nanoparticles. What we did is you see we have dispersed the particle on top of a glass, on top of a silicon surface. And this is, we have not analyzed, this is the preliminary rate. You see, this is fluorescence intensity changing copper particle. This is all nanoparticle. And this is the Bhasm particle, metallic Bhasm. So you see this is nanoparticle. This signature is showing that this our sample residue contains nanoparticle, and also large variation in particle intensity. So you see this is large particle. The error is something 18%, even sometimes is very high, 20-25%. If you put large amount of nanoparticle, even if particles are there, but if they are if you put in the large amount, the absorption also take into account. The absorption also comes into account. Then the intensity also decreases. Same particle, everything is same. Here we slightly we have dispersed, here we have not dispersed, but put over large surface here. So now you will not see any particle size because the bulk, it is showing bulk type of behavior, but the absorption factor also very important. The intensity also because some of the particle nanoform. So we have also large variation in intensity and also absorption. So one should be very careful. So particle size, surface area, let's see the particle distribution have a significant intensity, especially the TXRF region. So now, yeah, this is important. Now coming to the end of my talk. So basically, this application. So we have applied because we have, this in India because we have Ayurvedic medicine system, which is a very good system because this is in ancient times is very quite popular, and so In Ayurveda, normally we consider two types of medicines. Basically, some of the medicines they are derived from the plant-based medicines. So they are collected. Some medicinal plants are there. In some cases, we prepare the medicine from the some metallic particles, Bhasm particles. Bhasm is nothing basically incineration of the metal into some from finer particle. Why we call it form? Every time we say Bhasm. So basically, a bulk metal transform into the finer particles, small particles, basically in the nanoparticles. So whether it is possible that we can allow the escapolosis technique in Ayurvedic medicine? So yes, so this is recently 2014, our Prime Minister basically in India, they have established a department, Ministry of Ayush, especially just to promote the research and development in the field of this our traditional medicine system, because it has a lot of potential. Because this system is not explored so far. Because this system was quite established in the ancient time, while this allopathic system was not there. And it was effective also. So, this Prime Minister, this photograph of the Prime Minister. So he is a very wonderful person. I would say amazing. Every common man feels connected with him. This is what the beauty of his personality. It is also true for me. So sometimes, yeah, and, I know because when we were struggling with the COVID-19 period, he efficiently managed the country, lead the country, especially while we were struggling this second difficult time, second corona wave, and we are out of this phase. So this is what. So basically, he provided a lot of effort, lot of support, whether how you can do how to basically what are the guidelines that you have to follow. So this is what we are really very thankful. So in that case, just to remember, so we decided why not we can also analyze. We can also, is it possible that we can allow the exfoliation technique in the analysis of this our traditional medicine system? So I will give you only one example of plasma, which we have recently done. And this is what we not published so far and unpublished results. So basically, this is what the concept, I don't know whether it's true or not, but this is what we are speculating. So whenever basically we transfer the materials into the final particles sometimes micro particle, sometimes also in the final particle, whenever it enters into body, it further divided to smaller size and finally transformed to nanoparticle. In nanoparticle form, basically it contains the surface area density is very large because the surface area of nanoparticle is very large. That means surface. So the capacitance of a particle, basically, the spherical capacitor. So capacitance is nothing basically radius. It's function of radius. So you can say C is equal to 4 pi epsilon into A radius. So it is the capability. The surface charge is very high on the surface. It can attach some of the particle. For example, it can attach with the gold water molecules. Because this particle always in the size of nanometer, so it might enter the cell of the body. And because this concept behind this medicine system, Ayurvedic medicine system, was to generate the material in such a way it should not harm the body. It should be inactive. It should be chemically should be inactive. It should not chemically react with the body. It should cure the body physically. And so this particle basically interact in the cell, and they by the electron transfer. This is what we have to concept. And finally, they come out from the body, and it is already proved by some of the other colleagues in the RC. They have proven that some of the medicine which have been given some Ayurvedic medicine, and it has by analysis of urine sample, they had showed that this has come out from the body. So just to confirm what is happening, so this iron bus, we have taken the iron bus from this Ministry of Ayush. So first we did the analysis of X-ray diffraction analysis. So X-ray diffraction show that iron bus basically it has magnetite structure Fe3O4. So Fe3O4 basically contains two phases, Fe2 and Fe3, Fe2 plus and Fe3 plus. So confirm. Then what we did, we then dispersed. This is medicinal grade sample. So we did this. We dispersed this particle into water, and then further basically dispersed into ultrasonic. And whatever the particle dispersed in the water, we disperse on the surface, and then we did the analysis of SEM. To see this SEM, so this particle, if you see the large emissions, final particles are there. Even this is agglomerate of the particle, but final particles are there. One I can see less than 600, 700. This is 700, but even this, consider this side, this is 500, 300. And this is what the fluorescence spectrum. You see the fluorescence clearly shows the hurricane. It also shows the zinc. The zinc basically, because the procedure of medicine procedure is slightly different. They use conventional procedure, so they allow different ingredient also. So this is coming from the some ingredient they have used, because I do not know what type of ingredient they have, right? So yeah, so just to analyze, also we disperse this particle, whatever that is, this particle, Gaussian particle on top of the substrate, and then we did the analysis. We allowed this fluorescence particle size 100 nanometer. If you see the shape is more or less a square, more or less a square. It's not well defined because the agglomerates are square. So we analyze, because so we consider a spherical shape, spherical rectangular shape. This 10 nanometer distribution also changed. The profile is changing. In one case, this is a rectangular profile, 10 nanometer distribution, particle size greater than 100 nanometer. In one case, we have considered the particle size distribution 10 nanometer. In another case, we have considered particle size 14 nanometer. So there is different. And another case, we consider then we change the shape also by achieving the same one. Then we did the analysis with the experimental rates. So experimental, we found that the experimental rates matching with the rectangular shape. And particle size is 14 nanometer. Average particle size varies in 14 nanometer. Also, particle size greater than. So there's a lot of variation in particle size. So you see this also 2 layer particle size. This first estimate. And then we did the analysis of XPS, so it's spectroscopy, just to confirm, because I was finding whether whatever I have shown by the X-ray refraction, whether it's correct or not. So XPS clearly shows that this iron particle contains Fe +2 +3, both. And then, so naturally, if you consider the natural this magnetite, natural magnetite usually contains the Fe3O4. So the structure Fe plus atomic concentration Fe3O4, so 1:3 ratio, I think. And so this is what, so this I have explained. So this is what, if you see, and we found by XPS analysis found that the +3 state, sorry, +2 state slightly higher than the +3 state. The concentration +2 state is slightly higher than the +3, which were not matching with the this magnetite structure, naturally occurring magnetite structure. So this is, I don't know why it is happening, what by the procedure. We have tried to explain why it is happening. So basically, conventional route, normally they allow. So what they do, they take the metallic particle, and then in the water atmosphere also allow the heat treatment, and the slowly the water reacts with the metallic surface and generate Fe2 oxidation. This is the oxidation process. So when the particle in the water and atmosphere interact with the iron particle surface, it generates Fe2O3. And further repeated exposure. So in Ayurveda they also allow the repeated exposure just to oxidize fully. So then if you allow too many repetitions, then you ultimately transform into Fe3O4 crystalline structure. And finally, again you allow another procedure, other procedure also another procedure. Then we final crystalline form. You can convert it to fine. So this is Fe2O3. Now this is the reduction step. We realize because the Ayurveda normally there is a rigorous procedure they allow. In one step, sometimes they allow the oxidation process, and they also allow different different elaborate procedures. They put the material into the closed environment, closed vessel environment. So we predict that during the closed environment, normally the carbon monoxide generated from the heat treatment basically interact with the particles which were generated in the oxidation step. So this, what happened is this Fe2O3 particle in the presence of carbon monoxide slowly it reduced and it converted to F3O4 and CO2 is gone. And repeated procedure again convert Fe3O4. Correct, completely. I think I have done mistake. Okay, sorry. So this is Fe3. Finally, we are obtaining the Fe3 particles. So after the COs, whenever the CO interact with Fe3O4, so basically this CO2 is come out, and finally, so finally Fe2O3 finally convert into Fe3O4. Again, CO another reduction step. So again, the CO2 interact with the Fe3O4, and it again convert the top layer of the FeO. So that's why in the bus particle we realize there is some FeO, the +2 state slightly higher than the +3 state, because this is naturally occurring. Fe3O naturally, Fe3O4 have some natural ratio of the P+2 and +3, but in Boson case we have slightly higher amount of +2 state, and this is the this is what we predict. This is the probable procedure, because they use the elaborate procedure for doing the preparation. So it might be this. So both the by controlling the redox and oxidation process, so there is some kind of medicinal properties. So this Boson particle, this low Boson particle or metallic iron was basically used for the treatment of anemia, because our body is basically, because you already know, because whenever the hemoglobin, our body stores the iron in +3 state. You know this ferritin. Ferritin is a protein structure, and ferritin basically stores the iron in +3 state. And when if the iron is +3 state, it cannot bind the oxygen in our respiratory system. So it has to come into the +2 state before going to our lungs. So this is what our internal structure basically. From the ferritin, whenever it enters into the bloodstream, it converts into the +2 state, and then +2, if it is in the +2 state, it easily binds the oxygen in the lungs, and then it finally transport to the different part of the organ. So this is the iron hematology, basically iron metabolism is completely different, because it is not necessary if you are giving the medicine, it doesn't mean that it is the blood. Basically, it can cure the anemia or something, because it depends on how much storage of you have the iron storage, how much basically in the current, basically how much body utilizing the iron, and how much in the storage form. But in the metallic Boson iron was, we realize normally in the allopathic medicine they give the ferrous compounds. So ferrous compound is nothing, basically they contain the +2 state. But we realize this in this allopathic medicines they are using some +2 magnetite structure. So it contains both +2 and +3. So might be +2 because it readily available +2. So it may be useful for the immediately. And there are reports also, and several published papers are there. They show that whenever you allow this iron Boson to animal trial, and they also done human trial, immediately you have some relief from the anemia, and immediately the level of blood increases. So because the magnetite structure is basically magnetic, so just to confirm, because this is a medicinal system, just for our curiosity we have, because already we are doing several analysis, temporal Boson, basically copper compound. This is calcium compounds, Boson, lead compounds. And you see, this is the see, we allow a small magnet. So use the sunk Boson, basic calcium carbonate sample structure. So there's nothing is there. And this is copper compound. You see, we allow the magnetic field. It's a small magnet, very low magnetic field. And this is again lead compound. So there's nothing so. And this is the low Boson, which makes sense. And when we did, you see this, because magnetic structure. You see, this is what it immediately attracts. It has some structure. So it is magnetic. Confirm this. So finally, this is okay. Now, thank you very much for all of you for your attention. So this is what I've explained: particle size, how it can be useful for our traditional medicinal system. Because we have a lot of, because now we are thinking that it's real application. If I have generated something, some know-how, if I can use it for our medicine system, because this information is not available at all. because this is our system, because it's not explored so far. So I think there's a lot of scope if we allow this conventional medicine system in the modern techniques with the modern system. Thank you very much. So if you have any questions, please ask.
Yes. Thank you so much for this impressive broad overview of all your work and beamline capabilities. And I'm sure there are questions.
I have one question.
Yeah.
Okay. You have shown us a very interesting spectrum in the early stage of your talk. It was PB L alpha and L beta. It's just after this some silver K alpha, some
yeah, I have taken silver.
And yes, this one, the next one. Yes, it's a PB L alpha and L beta.
Yeah.
So the L beta is stronger than L alpha.
Yeah.
So this kind of thing is sometimes happen because of the particle size effect or self-absorption effect, or sometimes the ion K alpha, the sun peak is just overlap the L beta or something like that. So my question is, what is happening in here? Why the L beta is stronger than L alpha? It's my question. Particle size or surface roughness?
Particle size, basically, what is happening with the flow, because this is spectrum. This is typical example spectrum lead. Just I want to show that whenever you do the analysis, this is example spectrum because it's nothing linked with the particle size.
What is the sample here?
Yeah, there's nothing. This is spectra, simple spectra. This is nothing. Basically, bulk sample. It's not particle size.
And this is not the total reflection.
Yeah, nothing.
Is this total reflection?
No. It is not neither related to the total reflection, neither related to the flows, etc. Just I want to show how much complexity is there while you do the analysis.
Or is this the wavelength dispersive or energy dispersive?
Energy dispersive. This is energy dispersive.
Usually, sometimes wavelength dispersive, the L beta is a little bit stronger.
I completely
agree. And you have shown us some X-ray real sample spectrum just after this. I'm not sure which one. And its L beta was weaker than L alpha. So it's very strange.
Which one?
It's my not you have shown it's a log scale some real spectrum maybe afterwards.
This one?
No, afterwards you have shown us I'm not sure. It's a 500-year-old tile. It's a tile spectrum of 500 years old. Yes, this one. So
this one, okay, but yeah.
Yes, PB L alpha is a little bit stronger than PB L beta. So
alpha,
it's very strange.
Yeah,
it's my question.
Yeah, I understand. Yeah, because this tile sample, they don't want to break the sample. So we put the whole sample in the beam path. It might be because some of the absorption effects of the because the fluorescence intensity again, because this fluorescence intensity might be absorbed by the core because it's an over layer on top of the layer because we have some coating of the iron covert nickel. So L alpha maybe.
This sample contains the iron, but its concentration is not so high. That means the sun peak is not overlapped.
Sun peak maybe there.
Maybe iron sun peak is not overlapped to.
This sun peak, iron sun peak is not. You see the iron K alpha.
Yeah, and the iron sun peak is twice maybe 12 kilo electron volts.
Yeah.
So it's about the red L beta.
Yeah, it will come over here. You're right.
Yeah. But so the maybe if you find the reason, please inform me.
I understood. Yeah, because this is log scale. There may be some peak may be there because this iron, cobalt, nickel is there, lead is there. So this cobalt iron, if you consider about 6 point, how much is it? So
maybe this problem is very difficult, and
it is
quantitative analysis.
Yeah,
we must
that's
solve this.
This is what we
important.
Yeah, sure. This is what we highlighted. You are rightly pointed out. You are correctly pointed out. Spectrum fitting is main problem during the quantitative analysis. If you rightly fit the spectra, correctly analyze the spectrum, and correctly determine the intensity of different peaks, then you can definitely determine the concentration very precise. And this is what we struggled because we realized in you see this IA fitting, this IA analysis, because now this is now it is not easy because because we were facing the problem because we have because some of the peaks are very small and some of the peaks are mixing with others. So that's why we could not, because we were using PyMC software. PyMC is not okay, it is good software, but I would say if you consider too many things, because if you put L alpha, L beta, if you consider some peak also, there are several options out there. You can allow some peaks, you can allow the K beta peaks, you can allow over mixing. So if you, even if it is not there, if you put particularly
okay, maybe someone has another question.
Yeah, sure.
Yeah, thank you.
So if you have any doubt and questions, you can also ask me. You can send me email also.
Okay, very good. Yoon, you want to?
Yes, I have another question. You have shown us the Ayurveda medicine.
Yeah.
So what kind of toxic elements you find in the...
Yeah. So this is very good. I think I would say this is very interesting questions. Normally, this was it is thought that basically Ayurvedic medicines they basically in the system they use the toxic medicines, toxic elements. So Ayurveda is not a only branch. Ayurveda has two branches. Some of the medicines they are derived from the plant-based medicine. Some medicinal plants. So plant has three parts: root, shoot, and fruit. Some of the medicine they are derived from the root part. Some of the medicine derived from the shoot part of the plant, and some of the medicine they are derived from the fruit part. And they have different properties. Like I have shown for the coconut water, it contains a lot of minerals. And in one branch of science where Ras Shastra is there, so for very dangerous basically diseases or complex diseases where this simple medicine system doesn't work, and this system is unexplored, I would say. So in earlier days they were also using heavy toxic element. So heavy toxic element, normally bulk properties are toxic, but I don't know whether sorry. Can you? Sorry. Can you see my screen now? So we assume that this particle, this contains the so bulk property. For example, you have the bulk particle. Then you say some toxic particles are there. So I'm giving some example. Very good example. So what I will say, I have reduced some parts. Again, some material. I have reduced. Again, some material. I have removed some material. So, for example, if the particle is something like this, I would say this is the particle, and I remove this is bulk particle. I would say 110 micron. And if I remove some of the material from here, again remove some of the material from here and from here. Now it is transferred into nanoparticle. So if I show the band structure that means Bloch's theorem, you know, I'm going to the physics part. Sorry. So Bloch's theorem say if you see the band structure, because the several atoms are here, so atoms basically the atoms overlap. So there is force basically atoms, several atoms, two atoms like this one, and there are overlap regions. So there are basically structure if you bend level, you see K cell and cell again means like that. and then you have continuous band of states. So if you consider this particle, so particle, if you see the particle, if you have, because I have removed few atoms, another few atoms, then you see the band structure is the the band structure is basically discrete. You have only few layers. Well, another word I can say that when the material transforms into bulk material to nanomaterial, is its chemical structure, chemical properties, physical properties, and band structure, electron properties also changes because we have removed particle. Because now, for example, if you have a 10 nanometer particle, the band structure, for example, quantum nanodot. Quantum nanodot is nothing basically because the band structure of quantum nanodot is completely different from the bulk material. That its structure is basically different because its band structure is a discrete structure. So what happens? Now this particle is there. If we have so the band structure something, field structure something. Now the Fermi level, and you can say this band. Now this level is discrete, or it is not continuous. This is not conduction band is not continuous. It has some kind of band structure. So electron can easily, not very theoretically, I would say. So I think it is a lot of, it will be quite mathematics things, but I would say the band structure also change because here only 100 particles are contributing. So electron property, nanomaterial chemical property are changed. That means if a particle is toxic in nature in the bulk form, it is not necessarily means that it will be also toxic in the nano form. It may be different. Its property may be different. Similarly, vice versa also true. That means if a particle in nano form is bulk form is not toxic. For example, iron is not toxic in bulk form. It may be toxic in the nano form because the electron structure is completely different. Its chemical reactivity may be different. So this is because we do not know, because why were an earlier time we were using the toxic materials in the as a medicinal thing, and why they were working. So for example, normally some of the materials they can, for example, iron, this copper, sunplasm is nothing basically. It is a some calcium compound derived from the sea waters, from the sea animals. So they also show medicinal properties. Similarly, iron basically used for the anemia treatment, and iron, this is some of the medicine which are derived from the. I'm just describing this metal particle, which medicine which are derived from the metallic component. So lead, for example, they use lead, but lead is some of the people they have analyzed lead state, the structure of lead, and it is not in toxic form. But this is the reality because people they also consume, but they have done the animal trial, but it realized it doesn't show the toxic property. But this is what the modern concept, because people say that okay, this is not, because whatever we see the bulk property, and we assume that this will also be the same in the nano form. But because we have analyzed, we have realized this because we in our medicinal system we use a common term bhasm. So bhasm is nothing basically transformation of a bulk material into nano form. And with the concept that it should not interact with the body, chemical. It should interact physical. And it has to come out from the body. It should be completely, it should not harm the body. This is what the concept. So this is what we were, because we have started the work in this direction. So definitely, as soon as we have some progress and we realize something, definitely. So this is what,
probably Professor Kawai wanted to ask, could you see any dangerous element, toxic element in low wasp?
No, in low wasp, I could not see any toxic element. And he was saying that also in addition, Ayurvedic medicine, normally we also use some toxic element.
Yes, yes.
So toxic element, indeed we use toxic element. It is, this is the bulk property. We do not know whether it is toxic in the nano form. So this is what the Western concept of this. Because we are using toxic elements, it may be toxic, but we do not know whether it is toxic in nano form or not.
And
similarly,
moreover, it depends on the oxidation state. Which
exactly.
oxidation,
and which oxidation, because this Ayurvedic medicine, they use the elaborated process for their elaborated preparation procedure, where they allow several rounds of oxidation, several rounds of reduction processes, and by mixing different compounds also, finally material transform into such a form which basically, I would say, biologically friendly with the body. And this, I would say, this system is not very new. This is quite old system. This system was developed after understanding, comprehensive understanding this human anatomy, how the medicine is working, how this, because this is quite old system, and we have to, because it's our responsibility to revive how this, what is the potential feature, what are the hidden feature, and with the modern techniques.
Mhm.
So
Yes,
this
maybe
is what
I have
sorry.
another question.
Yeah.
So you've shown, I think, the experiments and the models analyzing the nanoparticles on top of multi-layers. Is that something that the support, the multi-layer support, that you commonly use, or
no, sorry. We do not use commonly, just to show the concept, just to prove the concept, whether this nanoparticle, this multilayer can be used for the analysis of particles size less than 10-20. Because
to me it appeared superior because there were more distinct features. Is that correct?
Which one?
So using this multi-layer support, my impression was it's easier to distinguish between nanoparticles because the oscillation are not more pronounced. Would you say that is the right impression, or
yes,
not?
yes. If you use the multi-layer, the oscillations are more pronounced, and also you can distinguish the oscillation. Because you see here, sorry, you can see the 6-9x. So you were saying
okay.
that, yeah. So multi-layer, basically application of multi-layer allow smaller size of particle. Sorry. Yeah. So
okay.
Yeah, no problem. No issue. Here in the TXRF vision, you have some structure. You have field size, 2D scientific n lambda, you can say. So the size of the standing field is slightly large. So if you have the particle less than the size of this, whatever, if you are sitting at particular angle, the particle size is less than that, the height of the standing field, then you cannot distinguish what is the size. So another method, you can generate this standing field by using this multi-layer, because if you increase the angle, the size of the standing field will be less.
Mm-hmm.
Because Bragg reflection occurs at higher incidence. TXR vision here, because TXR vision occurs at low angle, and the multi-layer Bragg region occurs at slightly higher angle. So D size is basically, D is nothing. So here D is basically the size of the standing field is lambda 2 sin theta. Lambda upon 2 sin theta. Lambda upon 2 sin theta. So if you have the slightly higher theta, D will be small. So D is small, then you can have the possibility that you can analyze the smaller size particle. And also you can distinguish the Bragg region. You can distinguish the features. This whatever you correctly pointed out. You can also distinguish the oscillation in the fluorescence profile.
Okay. Yes. Thank you. Are there more questions? Yes, I don't see any more questions. So let's thank the speaker again. And yes, I hope to see you all again on the 16th for the talk of INMA. And yeah, wish you all a pleasant rest of the day.
Thank you.
Thank you.
Thank you so much.
Okay.